Okay, so ionization energy is the energy required to remove. If we examine a period on the periodic table, those are the rows. We read them from left to right, just like we read the pages of a book. We're going to notice that ionization energy is going to increase as we move from left to right. So something on the left side is going to have a low ionization energy, and an element on the right side of the table is going to have a high ionization energy. All right, and if we think about why that is, if we think about where the cations are, they're the metals, and they're on the left side of our table. Cations lose electrons anyway. So if you want to get rid of something, you don't have to pay a lot for it. You don't have to use a lot of energy to get rid of it. On the right side, though, they're gaining electrons. They need more of them. So they're willing to pay for something because it's something that they really want or need. The group trend that we observe, so if we read from top to bottom, it's going to decrease as we move down the group. And basically, it's just because the ones at the bottom already have a lot of electrons. So they're a little bit more loosely bound, and they're easier to lose. Francium has 87 electrons. Lithium only has 3. It's easier for francium to lose that 87th electron than it is for lithium to lose 3, the third one. If you have your own periodic table, go ahead and drag it out because you're going to need it to be able to answer the next like learning check questions that we're doing here. All right. I want you to be able to look at a group of atoms, and I want you to be able to compare them in terms of whatever trend we're observing. In this case, the trend we're looking at is ionization energy. So if I were to kind of look at my periodic table, and you can look at yours, I'm drawing sort of like a blank one here on the board. And I wanted to look at ionization energy. Usually the best way to help yourself stay steady with this is to go ahead and put your arrows in place. We read from left to right. Well, what happens in our period? Well, we increase. So if we increase as we move from left to right, that means our small values are on the left side and large values are on the right side. And then if we go from top to bottom for our group, so this is ionization energy. Our large values are going to be on the top and our small values are going to be on the bottom because it decreases. So this helps us kind of put into perspective what we're looking at across the periodic table. So what you want to do next is you want to locate each of the elements that are in your group or your list. So I have Ba. Ba is about right here in group 2. So locate Ba. Then I have beryllium. It's up here at the top of group 2. Calcium. It's also in group 2. And then last but not least, radium. And it wants me to rank this from smallest to largest. Well, since they're all in the same group, let's look at our group trend. What happens is I move from top to bottom, I decrease. So the smallest of these is what? Ra. So now I have my smallest is rhodium, and then I would just simply read up my list. Rhodium, then barium, calcium, and beryllium. Does that make sense? All right, let's do another set just for some more practice here. All right, in this case, I've got silicon. So silicon's number 14. You can look at it. So we're on the rightish side of the table there, group 14. And then I have sodium, sulfur, and then chlorine. So sodium's number 11, silicon is 14, sulfur is 16, and chlorine 17. So once you've located all of these, let's decide, is this a period or a group? Well, we go from left to right, it's a period. And if I apply what I know, I increase from left to right. That means my largest values are on the right side, so my smallest values are on the left. Which of those would have the smallest ionization energies? Na. And then I would simply just read across. Sodium, then silicon, then sulfur, then chlorine. Questions? Okay. We'll come back and do our graphing exercises. All right. Next, then, we want to talk about ionic size or ionic radii. When we talk about atomic radius, we're referring to the size of an atom. If we're talking about ionic radius, we're referring to the size of an ion. And we're not going to do trends for these. We just want to know how to compare our neutral atom to cations and our neutral atom to anions. Cations are smaller than our neutral atoms. Anions are going to be larger. Uh-oh. All right. Let's think about the way that cations are formed. Cations are formed by losing electrons. If you lost weight, would you be bigger or smaller? Smaller, absolutely. Same thing here. So if a cation, you might have missed it, gives it away, loses its electron, then it's going to be smaller than its neutral counterpart. Anions, on the other hand, are formed when you gain electrons. So if you gain, you're going to be larger. So we have our neutral. It takes in or adds electrons to it. And boom, it becomes larger. So what you need to be able to do is you need to be able to determine if it's going to be a cation or an anion, and if it would be smaller or larger than its neutral atom. If it's a metal, if it's on groups 1, 2, and then 3 through 12, those are all cations. So they're all going to be smaller when they form cations. Anions get a little bigger. They're going to gain electrons and they're going to be larger. All right. Next trend, electronegativity. All right, for just a moment, we'll get off topic just a smidge, but it'll bring us to the topic we need to be on. Take a moment and think to yourself, who is the most attractive human being on the planet? I already know. Think about it. Who is the most... All right, so who's the most attractive human being on the planet? Who is it? None of y'all have an opinion on who's the most attractive human on the planet? Who? All right, I don't know who that is, but Margot Robbie. Anybody?
Johnny Depp.
Johnny Depp? I can get on board with that. Anybody else? I think it's got to be a tie between Damien from the Vampire Diaries and Shamar Moore from Criminal Minds. Yeah. For me, there's a tie there. Fellas, do you want to? Do you want to? You said nobody's attractive. I always like it. Usually, I get lucky, and there's at least one boyfriend girlfriend set in the classroom, and they say each other, and it's all like, "Aw," but not really. Or there's that one dude that always is like, "Me, I'm the one." So my point is I have you thinking about attractiveness, because let's say I don't know who's a popular singer with you people. Ariana Grande. Let's say she walked into school and needed a prom date. Do you think Ariana Grande would have a hard time getting a prom date here at Dark County High School?
Probably not.
Probably not. You feel like no, she wouldn't be struggling with that? All right. People would probably be like laying down, begging to be her prom date. I get that. And that's because she's attractive and she has money and wealth and fame, and she's Ariana Grande. Okay. Well, there's the same thing happens on our periodic table, but instead of people, we're talking about elements. Elements have different levels of attractiveness, just like people do. So electronegativity is what measures how attractive an element is, how likely it is to get the electrons. I guess, or just very, very attractive ones. Sometimes very, very attractive people aren't popular. All right, so the most electronegative, the Ariana Grande, the Ian Somerhalder, the Johnny Depp of the periodic table, is fluorine. Okay, fluorine is the epitome of electronegativity. It is the most attractive element. It can have any of the electrons from any other element, anytime, any place. It doesn't matter. All the electrons are like, oh, fluorine. Okay, they'll love the guy or the girl, however you want to put that out there. So if we think about where fluorine is located, if fluorine is the most electronegative element, and it is found right here on the upper right-hand corner of the periodic table. The closer you get to fluorine, the more attractive the elements. The farther you get from fluorine, the less attractive. So if we look at our whole periodic table, if we start over here at fluorine and we get as far away from fluorine as we can possibly get, who's the most unattractive element? Who's the farthest one from fluorine? Francium. Look at it. 87 over there. That is as far as you can get. Francium has an electronegativity value of 0.7. Fluorine is 4.0, perfect like a GPA. So the closer we get to fluorine, the more attractive we're going to be. And then, so if I am going to have a period trend, if I move from left to right, I'm getting closer to fluorine. So that means my electronegativity values are going to increase. If I move down my group, though, I'm moving away from fluorine. If I move away, that means my electronegativity is going to decrease. So if we were to follow the same steps that we did for ionization energy, the trend is the same. It has a different reason, but electronegativity is going to increase from left to right and decrease from top to bottom. If I move from left to right, I'm getting closer to fluorine. If I move from top to bottom, I'm getting further away. So my small values will be on the left side of the table, and my large values will be on the right side when I'm looking at the periodic table in terms of a period. Yes? Yes, fluorine will do that in a hot second. Oxygen's a good electron stealer. Chlorine too. They will suck them right into their net and keep them. All right, let's look at a set of of elements here, and let's see if we can rank these from smallest to largest. Again, the first thing that we have to do is we have to locate these on our periodic table. So here's phosphorus, it's about 15, or it's number 15, about right here. Then I have chlorine, which is 17. I have magnesium, which is number 12, and then aluminum, which is 13. If I want to know the one that's got the smallest value, it's the one that's furthest away from fluorine. Who's farthest from fluorine? Magnesium. That's it. That's all you have to do. So magnesium is going to be the smallest, and then it would be aluminum, and phosphorus, and then chlorine. Questions? I'm going to skip that one. All right. Our final trend is called electron affinity. Electron affinity is like the opposite of ionization energy. Ionization energy was the energy required to lose an electron. Affinity is going to be the energy required to gain that electron. Affinity means to like something. Like I have an affinity for coffee, and I have an affinity for snow days, and I have an affinity for naps. Those are all things that I like. I will spend energy to go get me some coffee in the morning. I will put forth effort to make that happen. If I don't think I can make it to work. I am completely reliant on caffeine.
Well, I drink tea.
Teas? Yeah, I don't drink tea too much during the day, except for these, the South Blend ones, which is more caffeine. I probably should lay off caffeine a smidge, but hey, here we are. Affinity, though, just means to like something. And if you like something, you'll spend energy to get it, correct? Anions really like electrons. And let's think about where the anions are on our table, the right side. Cations don't really want that outside electron. They really kind of want to get rid of it. So the affinity is going to be lower for cations than it is for anions. So we can look at our period and our groups. The period trend is it's going to increase as we move from left to right, and we're going to decrease down. All right, so we have our period trend and we have our group trend. And if you'll look, it has not changed. So ionization energy increases from left to right, decreases down. Electronegativity increases from left to right, decreases down. Electron affinity increases from left to right and decreases down. The trends are the same for all three of those. Atomic radius is the opposite of these. So most of the three of the four trends that I'm going to ask you to put a set of elements in order by are going to follow the exact same pattern. Atomic radius would be the one that is opposite against that. And we're going to practice those skills. Real quickly, see if you can determine the smallest electron affinity in this set of elements. Just look at your periodic table without me doing it with you and see if you can figure out which of these would have the smallest electron affinity. All right, what has the smallest? PB. That's right. If you were to locate all of those on the periodic table, which is what you do, the group trend is that it's going to decrease down, so the small ones will be found at the bottom, and the one closest to the bottom is PB. All right, what about this one? Which one would have the smallest electron affinity out of this set? All right, what do you think? Okay, potassium. That's right. If you locate it on the periodic table, that one is on the far left side. That's where our smallest values will be found. Any questions about our periodic trends? Okay. That is actually all of chapter 6 then. We're not finished for the day by any stretch, but this is the end of our information in our notes.